Hello students, today we are going to start with fifth part of chapter 13. Alkenes. Today's topic is alkenes. Acyclic unsaturated hydrocarbons containing a carbon-carbon double bond are called alkenes. They are also called olefins, since the lower members of this class produce oily products on reaction with halogens such as chlorine and bromine. That's why they are called olefins. Now, structure of double bond. The carbon-carbon double bond in alkenes consists of one strong carbon-carbon sigma bond with a bond dissociation energy and a weak pi bond with a bond dissociation energy of 251 joule per mole. The sigma bond is formed by head-on overlapping of sp2 hybridized orbitals, while the pi bond is formed by lateral or sideways overlapping of the two 2p orbitals of two carbon atoms. I am repeating again, overlapping of two 2p orbitals of the two carbon atoms. Now here is orbital diagram of ethene molecule. It's shown on the screen that there is sigma bond, and during sigma bond there is sp2 hybridization, and there is double bond. One is sigma bond and other is pi bond. Sigma bond is formed first, pi bond is formed after that. To have an effective overlap, the p orbitals move little closer. Therefore, a double bond is shortened than a single bond. Further, due to poor overlapping between the two p orbitals, and pi bond is always weaker than a sigma bond. Now, start with nomenclature of alkenes, as we have done nomenclature of alkanes in the first lecture of this chapter. Now start with, it starts from carbon atoms 2, as it is not possible to have double bond with a single carbon. That's why starting with carbon atom 2. Then name is ethene, C2H4. If carbon atom 3, propene, molecular formula C3H6. Similarly, if you have 7 carbon atoms, then it is called heptene with formula C7H14. 8, octene, C8H16. 9, nonene, C9H18. 10, decene, C10H20. As you have prepared for the series of alkanes, that is word root for alkanes, in fact, you have to also prepare the word roots for alkenes. Enes means double bond. Now, isomerism of alkenes. Alkenes show both structural and stereoisomerism, that is geometrical isomerism. Now, structural isomerism. Ethene and propene can have only structure, but alkenes containing 4 or more carbon atoms can show both position and chain isomerism. Here are 3 examples on the screen. First is but1-ene, and there is double bond at the first position, that is between carbon atom 1 and 2. But2-ene, here double bond is in the midway of 4 carbon atom. In fact, it is carbon number 2. Similarly, if one of the methyl group is adjusted as a side chain, then it will become 2-methyl prop-1-ene. And pay attention, here the lowest number is given to double bond, whatever is the position for substituent CH3. That's why in this example it is 2-methyl and not 1-methyl. It is 1-ene, not 2-ene. Okay, clear? Now, geometrical isomerism. A double bond consists of a sigma bond and a pi bond. The pi bond is formed by sideways overlapping of unhybridized p orbitals of two carbon atoms above and below the plane of carbon atoms. If now one of the carbon atoms of double bond is rotated with respect to the other, the p orbitals will no longer overlap and the pi bond should break. But the breaking of pi bond requires energy equal to 251 kilojoule per mole, which is not provided by collision of the molecules. Now, a pi bond prevents free rotation of the carbon atoms of double bond with respect to each other. Due to this hindered rotation, hindered means there is somewhat obstacle, there is somewhat restrictions during the rotation. The rotation is not free. The relative position of atoms or groups attached to the carbon atoms of double bond get fixed. Many substituted alkenes can exist in the two distinct isomers, which differ from each other only in the relative position of the atoms or groups in space around the double bond. For example, but-2-ene. Here is the example on the screen. Carbon double bond carbon, and here is 2-methyl group. If the 2-methyl group are on the adjacent position, then it is cis. If they are at the opposite, then it is trans. Trans means opposite. But both these isomers have same structural formula but differ in the relative arrangement of hydrogen atoms and methyl groups around double bond. Such isomers which have the same structural formula but differ in the relative spatial arrangement. Spatial arrangement means in the space, three-dimensional space of atoms or groups around the double bond are called geometrical isomers, and phenomena is called geometrical isomerism. Thus, geometrical isomerism is a space or stereo isomerism. Now, properties of geometrical isomers. Number 1, melting point. The melting point of a trans isomer is higher than that of corresponding cis isomer. So student, please pay attention for this slide as it is the back exercise question and various examples are set for this phenomena also. In the trans isomer, the two similar atoms or groups lie on the opposite sides of the double bond. Therefore, these molecules are symmetrical and hence pack well in the crystal lattice. On the other hand, in the cis isomer, the two similar atoms or groups lie on the same side of double bond. Therefore, these molecules are unsymmetrical and hence do not pack well in the crystal lattice. Intermolecular force of attraction holding the molecules of a trans isomer in the crystal lattice are much stronger than those holding the molecules of cis isomer. So, melting point of a trans isomer is much higher than the melting point of the corresponding cis isomer. For example, melting point of cis but-2-ene is lower than that of trans but-2-ene. The melting point of cis 1,2-dichloroethane is lower. Ethene is lower than that of cis 1,2-dichloroethene. So here is example of 1,2-dichloroethene. On the screen, picture is shown. For example, dipole moment of cis but-2-ene is 0.33 dBA, D for dBA, while that of trans but-2-ene is 0. Thus, trans 2-butene can be said to be non-polar. So, vector sum for the trans it will have some value, but vector sum it will get 0 if both trans, in case of trans, both the methyl groups are on adjacent on the opposite side, and for cis they are on adjacent side and they have some value, vector sum have some value, dipole moment mu has some value. In cis butene, the dipole moment of two carbon and methyl bonds are inclined at an angle 60 degree and hence have a resultant equal to 0.33 dBi. In case of trans butene, the two dipole moment being equal and opposite cancel each other, and therefore dipole moment of trans butene is 0. Trans-pentoene has a finite dipole moment, though much smaller than that of corresponding cis isomer. The dipole moment of carbon and methyl and carbon and ethyl bonds are not equal. These two dipoles opposes each other. They do not exactly cancel out each other, and hence trans-pentoene has a small but finite dipole moment. So cis form of it, this cis-pentoene is shown on the screen.